Have you ever just looked around and noticed how some things seem to follow a hidden rule? Like a pattern? From how a bouncing ball loses height to the way your savings can grow. There are these mathematical rules humming away under the surface. Well, today, we're going to decode that language. We're diving right into the super cool world of sequences and series. So, here's our roadmap. First, we'll cover the absolute basics. Then we'll jump into two major types of patterns: arithmetic, which is all about steady steps, and geometric, where things can get explosive. Then, believe it or not, we're going to tackle summing to infinity. And finally, we'll wrap it all up by showing how this stuff pops up in the real world.
All right, let's kick things off with Section 1, Patterns in Numbers. Before we dive into the really cool formulas, we just got to make sure we're all on the same page with the lingo. It all starts with just spotting a pattern.
So have a look at this. 2, 5, 8, 11. What's going on here? Yeah, you probably got it in like 2 seconds. We're just adding 3 every single time. And that simple, predictable rule, that is the core idea behind literally everything we are going to talk about today. Okay, so time for our first bit of official vocabulary. That list of numbers we just saw, that's what we call a sequence. It's just an ordered list. But what if we decided to add them all up? 2 plus 5 plus 8 plus 11, and on and on. Well, that's what we call a series. So sequence is the list, series is the sum. Got it? Cool. So now that we have the basics down, let's get into our first major category. Section 2, arithmetic patterns. The best way to think about these is just taking constant, predictable steps, kind of like walking down a path, one steady step after another. Now imagine adding up, say, 100 numbers in that sequence by hand. It would take forever, right? Thankfully, we have a shortcut. Now this formula might look a little scary at first glance, but I promise it's our best friend. S sub n is just a fancy way of saying the sum of n terms. This a here, that's just the very first number in our sequence. N is how many numbers we're adding up, and d is that constant difference we keep adding, the 3 from our last example. Okay, let's actually put this thing to work using our 2, 5, 8 sequence. Let's say we want to find the sum of the first 35 terms. We can just map our numbers right onto the formula. The first term, a, is 2. The common difference, d, is 3. And the number of terms we want to sum, n, is 35. All right, time for the fun part. Let's plug and chug. First, we substitute all our values into the formula. Now we got to handle what's inside the brackets first. So 35 minus 1 is 34. Okay. Then we multiply that by 3, which gets us 102. Add the 4 from the 2 times 2 at the beginning, and that whole bracket just becomes 106. See? Not so bad. All that's left is 35 divided by 2 times 106, which gives us a grand total of 1,855. Seriously, just think about that. Instead of sitting there with a calculator adding 35 different numbers, our formula got us the answer in a few quick steps. That's the real power of these things. But of course, patterns aren't always about just adding. Sometimes they grow a lot faster. This brings us to Section 3 and our second major type, geometric patterns. These are all about the power of a multiplier. And you can really see the difference here, can't you? Arithmetic on the left is a straight line. It's steady, it's predictable, you just add each time. But geometric on the right? Whoa, that's a multiplier effect. It starts off slow and then it just takes off like a rocket ship. That's what we call exponential growth. And you guessed it, we've got a formula for this too. Yeah, okay, it looks a little hairier, especially with that art of the power of n business in there, but don't worry, the core idea is exactly the same. It's a powerful shortcut to save us from a massive headache of manual calculation. Let's try an example. Imagine we have the sequence 2, 8, 32. You can see we're multiplying by 4 each time. Let's find the sum of just the first 7 terms. Okay, so our first term a is 2. Our common ratio r is 4, and n, the number of terms, is 7. Simple enough? So let's plug these in. Now, here's where geometric series really show their muscles. We have to calculate 4 to the power of 7, and that number gets big, fast. It's 16,384. That's our rocket ship taking off. After that huge step, the rest is pretty easy. We subtract 1, divide the result by 3, and then finally multiply the whole thing by our starting number, 2. And the final answer is, get this, a whopping 10,922. Let that sink in. We only added 7 numbers together, and we're already way over 10,000. That is the incredible power of that multiplier effect in action.
Okay, so this is where things get really wild. Section 4, what happens if a sequence never ever ends? I mean, can you actually add up an infinite number of things and get a real finite answer? It sounds totally impossible, right? But it turns out sometimes you can.
The whole secret comes down to these two ideas, convergence and divergence. A series converges if the numbers you're adding get smaller and smaller and smaller, so small that the total sum actually closes in on a specific number. For geometric series, this only happens when your multiplier r is some fraction between -1 and 1. If r is bigger than 1, the numbers get bigger and the sum just explodes towards infinity. We call that divergence.
And here is the truly crazy part. If a series does converge, the formula to find its sum is the most beautiful, elegant one we've seen yet. The sum to infinity is simply the first term a divided by 1 minus the common ratio r. That's it. An entire mind-bending, infinite process captured by a tiny bit of simple arithmetic. How cool is that?
Let's see it in action. Check out this sequence. 5, then -1, then 1/5, and so on. Our first term, a, is obviously 5. To find the ratio, we just divide any term by the one before it. So -1 divided by 5 gives us our ratio r, -1/5. Since that's a fraction between -1 and 1, we know for a fact this thing is going to converge.
Okay, calculation time. We substitute our values in, we have 5 on top. On the bottom, we have 1 minus our ratio. Now, you got to be careful with the signs here. It's 1 minus times -1/5. So the two negatives cancel each other out, and it becomes 1 plus 1/5, right? That gives us 6/5 on the bottom. So now our problem is 5 divided by 6/5. And remember, when you divide by a fraction, you just flip it over and multiply. So it's 5 times 5/6.
And that gives us our final answer of 25/6. Just pause on that for a second. We added up an infinite number of terms, and the grand total is this one simple, neat little fraction. It's just incredible when you think about it.
So you might be thinking, okay, this is some cool math, but when would I ever actually use this? Well, for our final section, let's bring this all back down to earth and see how these tools help us understand something you've definitely seen before. You know those repeating decimals, like 0.1666 and so on? Well, it turns out that's actually an infinite series in disguise. Check this out. We can split it into two parts, the 0.1 and then the repeating part, which is 0.06 plus 0.006 plus 0.0006 and on forever. Now look at that repeating part. That's an infinite geometric series. The first term is 0.06 and the ratio is 0.1. So we can use our sum to infinity formula on just that part and it gives us 1/15. All we do now is add our two pieces back together, the 0.1, which is 1/10, plus the 1/15 we just found, and it adds up perfectly to 1/6.
So there you have it, a real-world use for summing an infinite number of things. It just goes to show you that these formulas aren't just abstract ideas. They're the language the world is written in. So it makes you wonder, right? What other parts of our world, from the way money grows in a bank to the spirals in a seashell, are secretly built on these same simple, predictable rules?
Hey everyone, and welcome. Today, we're going to break down something really powerful called linear optimization. Now, I know the name sounds kind of technical, but trust me, it's not just for math whizzes. At the end of the day, it's all about answering a question we all face. How do you make the absolute best choice when you don't have unlimited resources? Let's dive in. I mean, really think about it for a second. Every single day, we're dealing with limits, right? You've only got so much time, so much money, so much energy. So the big question is, how do you take what you've got and get the best possible outcome? I'm not talking about a pretty good outcome, I mean the mathematically perfect one. That's exactly what we're going to figure out. So to really wrap our heads around this, we're going to use a simple and delicious example, a bakery. Imagine our baker has a set amount of time and a limited supply of flour. The puzzle is, how many cakes and how many cookies should they bake to make the most profit possible? This is a classic optimization problem. So first up, we've got to define our goal. Before we can even think about finding the best answer, we need to know in no uncertain terms what best actually means. For our bakery, it's simple. Best means the most profit. Okay, so this formula right here, this is what we call our objective function. It's the heart of the whole puzzle. It's just our goal written down as math. We're saying our total profit, let's call it P, is equal to $5 for every cake, which is X, plus $3 for every batch of cookies, which is Y.
That's it. Our entire mission from here on out is to make that number P as big as we possibly can.
Now, if our goal is to maximize profit, you might be thinking, why not just bake 1,000,000 cakes? Well, that's where our limits come in. In this next part, we're going to map out the rules of the game, all the things stopping our baker from just making infinite cakes and cookies. In optimization, we call these limits constraints. A constraint is just a rule you can't break, written out in math. You can think of them as the walls of our playing field. Any plan we come up with, any combination of cakes and cookies, has to fit inside these boundaries.
And this is how we turn those real-world limits into math. Let's break it down. Our first constraint is time. We've got 12 hours. If each cake, X, takes 2 hours, that's 2X hours. And each batch of cookies, Y, takes 1 hour, so that's 1Y. When you add them up, 2X plus 1Y, the total time has to be less than or equal to 12. You can't use more time than you have. It's the exact same logic for flour. 3 units per cake plus 1 unit per cookie batch has to be less than or equal to the 15 units we have in stock. This is our rulebook.
Now, the cool part is when you actually draw these rules out on a graph, they create a specific shape. The area where all the rules overlap, where you're not using too much time and you're not using too much flour, that's called the feasible region. Every single point inside this little zone represents a possible plan our baker could actually pull off.
So, we have this entire region filled with possible answers. Do we have to check every single one? No way. And this is where the real magic comes in. We're about to show you an incredible shortcut that makes this entire thing possible. And this right here, this is the secret sauce. This is the core idea of linear optimization, and it's a total game changer. What it means is that the absolute best answer, our maximum profit, will always be hiding at one of the corners of that shape we just drew. We don't have to check the infinite points inside, just the handful of corners. It's the ultimate shortcut.
So this amazing insight gives us a super simple 3-step playbook. First, we just need to find the exact locations of those corners on our graph. Second, we take the numbers from each corner and plug them into our profit formula. And third, we just compare the numbers. Whichever one is biggest, that's our winner. It's really that simple.
All right, time for the main event. We have our goal, we have our rules, and we know we only need to check the corners. So let's roll up our sleeves, crunch some numbers, and find our baker's perfect plan.
By figuring out where our constraint lines cross each other on the graph, we find these 4 corner points, or vertices. The perfect plan, the way to get the most profit, has to be one of these 4 options. It's guaranteed. So now, all we have to do is test them.
Let's start with the most obvious one, the corner at 0, 0. This one's easy. It just means we bake 0 cakes and 0 cookies. So we plug that into our formula. 5 times 0 plus 3 times 0. Yep, that gives us a big old profit of 0. Not exactly a winning strategy, but it's a valid corner, so we have to check it. Okay, next up, the vertex at 5, 0. This plan is basically go all in on kicks. We make 5 cakes and 0 cookies. Let's run the numbers. $5 times 5 cakes is 25, plus $3 times 0 cookies is 0. Total profit, $25. Okay, much better than 0, but is it the best we can do?
Now for our third corner, 4, 6. This is a mix and match plan. We bake 4 cakes and 6 batches of cookies. Let's do the math. 5 times 4 cakes gets us $20, and 3 times 6 batches of cookies gets us another $18. We add those together, 20 plus 18 is $38. Ooh, okay, now that's our new leader.
We've got just one last corner to check, 0, 12. Let's call this the Cookie Monster plan. 0 cakes, but 12 batches of cookies. So 5 times 0 is 0, plus 3 times 12, which is 36. That gives us a total profit of $36. A very good day, for sure, but just a little shy of our leader.
And there we have it. Let's look at the final scoreboard. When we lay out all the results, there's a clear winner. That $38 in profit we calculated from the corner 4, 6 is the highest number on the board. We've found our optimal solution.
So the single best answer is bake exactly 4 cakes and 6 batches of cookies. This specific combination will squeeze every last penny out of our resources, giving us the maximum possible profit of $38. Any other plan we could have come up with would have made less money.
So solving a bakery puzzle is pretty cool,
But what's really amazing is that this exact same logic, this same process, is used to solve huge, complex problems in the real world every single day.
Think about a farmer. Their goal, their objective function, is to get the biggest possible field. But they have a constraint. They've only got 300 meters of fence. By using this exact same method, define the goal, map the limits, test the corners, they can figure out the perfect dimensions for their field to get the absolute most area. It's the same puzzle, just with different pieces.
So, if you remember just one thing from all this, let it be this three-step process. First, define. What's my goal and what are my rules? Second, identify. What are the corners of my playing field? And third, test. Run the numbers on those corners to find the absolute best path forward.
And that leaves me with one final question for you. Think about it. Whether it's managing a project at work, figuring out your personal budget, or even planning your week to be more productive, what in your world could be optimized? Thanks for watching.
Hey everyone, and welcome. If you've already gotten the hang of solving for x in a quadratic equation, we'll get ready to take it to the next level. Today, we're diving into quadratic inequalities. And this is cool, because the answer isn't just a number or two, it's a whole range of possibilities. Let's jump in and break down exactly how you can master them.
So here's our game plan for today. We're going to start with the absolute basics, what these things even are. Then we'll explore two really powerful ways to solve them, first with algebra, then with graph. After that, we'll level up and tackle systems of inequalities. And finally, we'll bring it all home and see how this math shows up in the real world.
So what exactly are we talking about? You're probably super familiar with quadratic equations, right? That classic ax squared plus bx plus c equals 0. Well, inequalities take that equal sign and swap it out for something way more flexible.
So instead of that one lonely equals sign, we get these four characters: greater than, less than, greater than or equal to, and less than or equal to. Now this might seem like a small change, but it completely transforms the problem. We are no longer looking for one or two specific points. Nope. We're on the hunt for an entire range of numbers, a whole interval where the statement is true.
All right, let's get our hands dirty with the first method, pure algebra. This is the super precise, step-by-step way to nail down our solution set, and it all hinges on one absolutely critical idea.
And that idea is something called critical values. I want you to think of these as fence posts. They're the points where our expression actually equals 0, and what they do is divide the entire number line into different zones. These zones are the key, and the critical values are the boundaries that create them.
This is our 5-step roadmap. First, get everything on one side so it's set to 0. Then, we factor it down. Step 3, find those critical values, our fence posts. Step 4 is the fun part. We test the regions they create. And finally, we just state our answer. Let's see how it works with a real example.
Okay, let's put the process to the test with this one. X squared minus 2x minus 15 is less than 0. Now, step 1 is already done for us, which is nice. Everything's on the left. So what's next? Time to factor. So we need to think of two numbers that multiply to negative 15 and add up to negative 2. Okay, that's got to be positive 3 and negative 5. So our factored inequality is x plus 3 times x minus 5 is less than 0. Now we can find those all-important boundaries.
Finding our critical values is easy now. We just pretend it's an equation for a second and set each factor to 0. So if x plus 3 equals 0, then x is negative 3. And if x minus 5 equals 0, x is 5. And there they are, negative 3 and 5. These are our two fence posts, splitting the number line into 3 distinct regions that we now need to go and investigate.
Okay, now for the most important part, testing these intervals. Let's just pick an easy number from each zone. First up, the region where x is less than negative 3. Let's try negative 4. We plug it into our factored form. Negative 4 plus 3 is negative, and negative 4 minus 5 is also negative. And what's a negative times a negative? It's a positive. Is a positive number less than 0? Nope. So that whole section is out. Next, the middle zone between negative 3 and 5. The easiest number to test is always 0. So 0 plus 3 is positive, and 0 minus 5 is negative. A positive times a negative gives us a negative result. Is a negative number less than 0? Yes, it is. Bingo! This interval is definitely part of our solution. Last one, for x greater than 5, let's test x equals 6. 6 plus 3 is positive, and 6 minus 5 is also positive.
Positive times positive is positive. Again, not less than 0, so that region is out too.
So let's put it all together. Our original inequality was less than 0, right? We were looking for a negative result. Our testing showed that the only interval that gave us a negative result was the one right in the middle. So our solution is all the x values strictly between -3 and 5. That was the algebraic method. It's super precise, very procedural, but now let's look at a completely different way to think about the exact same problem. We can turn it into a picture. Moving to a graph gives you this amazing, intuitive feel for what's really going on. Think about it. The graph of y equals x squared minus 2x minus 15 is a parabola, right? It's a U shape that opens up. And where does it cross the x-axis? Exactly at our critical values, -3 and 5. Since our inequality is less than 0, we're literally just looking for the part of the graph that dips below the x-axis, and you can see it plain as day. That happens exactly between -3 and 5. It's the same answer, just seen from a whole new angle. So you've got two fantastic tools in your toolkit now. The algebraic method is your scalpel. It's precise, it gives you the exact boundaries, no guesswork. But the graphical method, that gives you the intuition. It helps you see why the solution is an interval. And the best part? Both lead you to the exact same result. Okay, so we've totally mastered a single inequality. You ready to kick it up a notch? What happens when you need a solution that satisfies two different quadratic inequalities at the same time? This is where things get really interesting, because now we can model much more complex situations.
So check out this system. We've got one parabola opening upwards and another one opening downwards. The solution here isn't just a line or an interval, it's an entire region. Imagine shading the true area for each inequality. The solution is the space where those two shaded areas overlap. But to define that region, we first need to figure out exactly where these two parabolas cross paths.
All right, to find out where they intersect, we just need to see where they're equal. So we set the two expressions equal to each other. Now our goal is to get this into a standard quadratic form, so let's move everything over to the left side. We'll add 3x squared to both sides. That gives us 7x squared. Then add 7x to both sides, giving us 12x. So now we have 7x squared plus 12x equals 0. This is actually pretty easy to factor. We can just pull out a common x. That leaves us with x times the quantity 7x plus 12 equals 0. And from here, our two intersection points just pop right out. Either x equals 0 or 7x plus 12 equals 0, which means x equals -12/7. These two x values we just found, -12/7 and 0, are the horizontal boundaries of our solution region. If you picture the graph, this is the slice where the shading from both inequalities would overlap. So the solution set for our system is all the x values between -12/7 and 0. I know, this can feel a bit abstract, but these tools are incredibly useful for solving actual, tangible problems you might run into. Let's take a look at how we can translate a real-world request into the math we've just been doing.
Okay, here's our scenario. An artist has some very specific constraints for a new canvas. The area has to be 80 square feet at most, and there's a specific relationship between the length and the width. Our job is to turn these words into a mathematical inequality. Let's break it down step by step. We know area is width times length. We're told the length is 2 feet less than the width, so mathematically, that's just w minus 2. So the area is w times w minus 2. The artist needs that area to be 80 or less, which is our less than or equal to sign. So w times w minus 2 is less than or equal to 80. Now we just expand it out and move the 80 over, and we get w squared minus 2w minus 80 is less than or equal to 0. And look at that, it's the exact type of inequality we now know how to solve.
So we factor it, and we get w minus 10 times w plus 8 is less than or equal to 0. This gives us critical values of 10 and -8. The algebra tells us the solution is any number for w between -8 and 10. But, and this is so important, we have to do a real-world check. Can a canvas have a negative width? Absolutely not. So we have to throw out that whole negative part of the solution. The actual practical answer is that the width can be anything greater than 0 up to and including a maximum of 10 feet. And it's not just about things like area. Get this. Remember that system of inequalities we solved a minute ago? The one with the two parabolas creating that cool lens shape? Well, that's precisely how designers can model the curve of a necklace or the shape of an eye in a drawing. The abstract math we did on the screen can directly describe a beautiful physical form. So,
From figuring out the perfect size for an artist's canvas to defining the elegant curve of a satellite dish or a projector lens, the math of quadratic inequalities is truly all around us. We've seen how to solve them with precise algebra and how to understand them intuitively with graphs. The real question is, now that you have these tools, what problem are you going to solve? Thanks for joining me on this one.